I have 3 tricks for Taylor series, and that'll do it. 3 tricks. I have a couple for you to try, and then that'll do. So these are tricks which make it so that you don't have to do a bunch of derivatives. Remember, to find the Taylor coefficients, you take derivatives. Taylor series coefficients are, the formula is this, 1 over n factorial, f the nth derivative at a, where a is the center, right? This is a formula for the Taylor series coefficient. So in theory, you could start with any function and just find the coefficients using this formula. The problem, though, is these derivatives are often very hard to compute. Because you have to somehow do every derivative, the nth derivative. For some functions, even the first derivative is a real pain to calculate. Maybe you would have to use the quotient rule or whatever. And the second and third would even be more complicated. So that's why we have some tricks. So these are tricks can sometimes can avoid these derivatives, right? So the purpose of what we're talking about today is if you are trying to find the series, but you don't want to do those derivatives, which, let's be honest, usually I don't want to do those derivatives, right? If there's a better way to do it, then I'm interested in the better way. By the way, I don't know why, the video from last class about Taylor series got a lot of views on YouTube. Well, a lot meaning like 250, which is much more than our typical class videos. Yeah, I don't know. Maybe one of you was hitting the refresh all night. Thank you for that. My account that I post them in just hit the monetization threshold, so I can quit this job, make 10 cents a day or something. Okay, tricks. The first of the 3 tricks is very simple. So a very easy one is add them. For example, how about let's find the series for e to the x plus 2 cosine x. The trick, which I will call add them, is just, well, we already know the series for e to the x and the series for cosine of x. And so we can just add them up. So what that looks like is this, like I said last time, I will expect you to have these ones just straight up memorized. I'll just write the first 3 terms. That's e to the x. Cosine x, I hope you remember, is similar to that, only it uses only the odd degree terms and it alternates the signs. So it's x, and then I'm going to sort of line them up because I intend to add them together. The next one would be plus 1/5, or 1 over 5 factorial x to the 5, and so on, all right? And I'm going to add them up. Now, actually, I want e to the x plus 2 cosine x. So can we modify this so that instead of cosine x, it says 2 cosine x? That you can just distribute 2 across everything. Distribute 2 across everything. It'll say 2x minus 2 over 3 factorial x cubed, etc. Right? And now I can just add them up. So e to the x plus 2 cosine x. The series, now this is kind of a pain to do if you're working with sigmas, but if you just want to write down the terms one by one, it's very simple. I'm going to add e to the x and 2 cosine x. So that's this one and this one, right? The one in the middle was just sort of an intermediate step. So the constant term is just a 1. That comes from e to the x, and there was no constant term from the 2 cosine x. So it's just the 1. Next, I have e to the x in the degree 1 term. E to the x gives me x. 2 cosine x gives me 2x, so the next term is 3x. We're just adding them up term by term. That 3x comes from x plus 2x. And then the next term is the x squared term. We don't get anything from the cosine, but we do get from the e part 1 over 2 factorial x squared. The degree 3 term, we actually have sort of a mixture this time. We have 1 over 3 factorial x cubed from the e to the x, and then minus 2 over 3 factorial x cubed from the cosine x. So this actually ends up being minus 1 over 3 factorial x cubed. And the reason, so where that came from was this was 1 over 3 factorial minus 2 over 3 factorial, which simplifies to 1 over 3 factorial. Right? And then I will just say plus dot dot dot. Or this is like the worst dot 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 I've ever written this semester. Do you see the pattern? The answer is not really, but I mean the pattern comes from adding these two things together. But it's not actually obvious how you would just straight up predict what the next one looks like. The even ones look the same as e to the x. The odd ones look like a combination of the e's and the cosines. All right. So if I, typical way that I would ask a question like this is say something like, write down the first 4 terms of the series for e to the x plus 2 cosine x. Then you don't have to worry about what exactly is the pattern over here because it's not easy to say. All right. This is adding the series, an easy trick in my opinion. Any questions about that one? I said I had 3. The 2 more are slightly more interesting and a little fancier. They are multiply them and divide them. They are going to be more complicated than adding them. So let's talk about multiplying them. This is like extreme FOIL. All right, let's try a series for, here's how I might ask this on the quiz or something if I want it to be very specific. Find the first 4 terms of the series for, how about 2 plus 3x times e to the x. And here they are being multiplied. All right. So the way we do this is by multiplying them, which ends up being some kind of extreme FOIL. So I'm going to first say, 2 plus 3x, you just sort of leave like that. But e to the x now is 1. I'm writing the series for e to the x. 1 plus x plus 1 over 2 factorial x squared, 1 over 3 factorial x cubed, plus etc. Now I think that is enough terms that I need to write. I want to end up with 4 terms eventually in the answer. And I think that this is going to be good enough for that purpose. And now we just have to do some kind of extreme FOIL. So what is it going to look like? It looks like you would, if, you have to imagine that this was only sort of finitely long, then you would just start with the 2, multiply through everything by 2, and then you go plus and separately multiply through everything by 3x. All right, this is how you would do this multiplication if you had to. And we can do the same thing. You should feel a little worried maybe that this is infinite, but actually all of the details work out in exactly the same way. So I am going to do a big FOIL here. I'm going to multiply everything through by 2 first. So this will say 2 plus 2x plus, actually that's, 2 over 2 factorial. 2 factorial is 2, and so that's just going to cancel. 2 over 3 factorial x cubed plus dot dot dot. That's what you get from multiplying through the 2. And what's inside the dot, this is important. These are all degree greater than or equal to 4, right? And so when it comes to my answer, which is supposed to have the first 4 terms, I don't actually care about any part of those 3 dots there because these are all higher order terms which will not appear in my answer. So we don't have to worry about what exactly is in the dots. And then plus, I'm also going to go through, distribute 3x across this whole thing. And that will say, so 3x times 1 is 3x. 3x times x is 3x squared. 3x times 1 over 2 factorial x squared is 3 over 2 factorial x cubed. 3x times the next one. Actually, you don't even have to do the next one, all right? These are all degree greater than or equal to 4 also, right? The next one would have been 3x times 1/3 x cubed, but that would have been something x to the 4, and I'm not going to care about that in my answer because I'm only supposed to write the first 4 terms, all right? This is basically all the work has been done, but to write the answer as a single series, you should rearrange these things, group together the powers of x. So my final answer then is 2 plus something x. Can somebody say what is it? 5x. Yeah, I got 2x from the first part, 3x from the second part, so 2 plus 5x plus, okay, 2 over 2 factorial x squared, and then over here I have 3x squared. 2 over 2 factorial is 1, right? This is just 1. So that is 1x squared plus another 3x squared. That's 4x squared. The next one is going to look a little nasty. 2 over 3 factorial plus 3 over 2 factorial. Is that anything? No, not really. I mean, you could try to simplify these fractions, but there's no that doesn't add together to be anything cute. It's just whatever it is. Plus dot dot dot. And everything in those dots is degree 4 or higher. So even though we don't know what the next terms look like, I mean, we could figure them out if we wanted to. We'd have to backtrack a couple steps and write down the higher terms. But we do know for sure the first 4 terms must look like this, because nothing else over here has power 3 or less. All right, so this is the multiplying trick. Any thoughts about that one? You can actually, I don't think we need to do an example of this, but you can actually do like a double infinite. You can do an infinite series here times another infinite series here. You still have to be a little careful about it, but everything basically works out the way you would want it to. For instance, if I wanted this series for e to the x times sine of x, you would do 2 series and then multiply the entire big series together. All right, I got one more trick. That was adding, multiplying. The last one, divide them. This is the most complicated one. But I kind of like this, actually. I don't know if you like. This is like extreme long division, all right? So I'm going to try, how about e to the x over x minus 1? All right, e to the x over x minus 1. I'm going to divide them, and you can really kind of do this just like in one step. Let's write, again, I'm going to write the first 4 terms. All right, so we are going to do a long division here. So I begin with e to the x. It's really this, right? X minus 1 divided into e to the x. But e to the x we're going to write as a series. So it's going to look like, I'm going to scroll down a little. Over here, the series, and would you mind, it's going to be easier, sorry. I'm going to write, instead of x minus 1, I'm going to write -1 plus x. You'll see why in a moment. And then the e to the x, I write the series. 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial. Because I'm going to be dividing here, it's going to be a little nicer if I write out. So that 1 over 6 is the same as 1 over 3 factorial. I'm just calculating the factorials so that we can divide easier in this division thing. All right. And now we are going to do the polynomial long division. The fact that this polynomial goes on forever really doesn't matter much at all. You can still do the usual polynomial long division thing because you start over here and you sort of keep going as you go. You could get more and more terms and do more and more, however many you want to do. All right, so let's do it. I hope everybody is feeling good about polynomial long division. What goes here? Yeah? -1. Yeah, I'm looking for something which will match this term with this term. Maybe this is a little weird because I think most people are used to doing polynomial long division sort of like this. I'm just making this up. Where here you're trying to somehow match the x with the x squared. What you need there is x. All right. Because of the way the power series works, you have to write it the other way around. You have to start with the constant term because there is no top degree that you can start at. And so I wrote both of them as starting with the constant term. And then what goes right here is -1 because that's what it takes to match this constant term with this constant term. All right. And then we multiply down. So to continue the long division, you multiply this thing by that and write it underneath. So I go, it's going to say 1 minus x, right? And then we subtract. The subtraction shall say x, well, the 1 and the 1 will cancel, right? And then we have x minus negative x. The answer is 2x. And then I bring down the next term as usual, 1/2 x squared. Hope I'm doing all right. I don't know how you like to write these things. I find actually it's very confusing to me if I put a little minus right there. It makes me very confused because actually if you're going to put a minus there, you should really kind of do that. And then I start worrying about, do you get 2 there or do they cancel there? The answer is you get 2. So I draw the line and I remember that the line means subtracting rather than adding. Anyway, that's what we get here. Can anyone say what's the next coefficient or what's the next term going to be in the quotient? Somebody else want to shout it out? Yeah.
Is it minus 2x?
Negative 2x. Yeah, I like that. It's because we are trying to match up -1 with 2x. And what do you need to multiply -1 by to get 2x? The answer is negative 2x. Great. All right, multiply it down. We get 2x and then minus x squared. I put my line there and we are going to subtract now. Minus 2x squared, sorry. Right? And now I'm going to subtract 1/2 minus negative 2x. That is 1/2 plus 2x. 2.5, you could say 2.5 if you like, or you could say 5/2 x squared. 2.5x if you prefer. All right? I hope we're doing all right. Are we going to just keep doing this forever? No, because I said just write the first 4 terms. So we need to do 2 more steps, and then we can put ... as if we know what the pattern is and be done with it. So let's do the next one. Somebody else? Can you say what's the next term going to go up top? Yeah.
-3/2 x squared. I did my math wrong on my paper. With -5/2 x squared.
-5/2 x squared. I like that. Great. Yeah, you're trying to match up this -1 with this 5/2 x squared. And you need -5/2 x squared. All right. Excellent. I forgot to drop down the next term, but 1/6 x cubed. Okay, multiply. We get 5/2 x squared as we wanted, and then plus 5/2 x cubed. Now the fractions get a little annoying. We subtract those things. And it should be a minus, not a plus. There. We are going to subtract 1/6 minus 5/2. Would you mind if I just say, 1/6 minus -5/2. That's 1/6 plus 5/2. X cubed. I wrote x squared here. X cubed. All right. You could try to add that up if you like in terms of sixths. 16/6, right? Something like that. 16/6. Okay, what's the next term? Somebody else? Yet another somebody else? One last time. It's the last time I'm ever going to ask somebody else. You're not somebody else. You're the same guy from last time. I recognize you. What else? I'm trying to match this coefficient of -1 with this coefficient, which is 16/6.
-16/6.
All right, yeah, -16/6 x cubed. Okay? Anybody want to do any more? No, you don't even have to like multiply it down or whatever, because our goal was to find just the first 4 terms. I say plus ... and that's the answer. All right. If you want to, you could calculate the next term, but it's not necessary based on what I asked. All right. I have 2 of these for you all to try, and then that will do it. Let's try. 2x plus 3 times cosine x and sine x over x plus 1. Both times, write the first 4 non-zero terms. See how you feel. I will remind us of the series for sine x and cosine x. You should remember these, but sine has even terms, sine has odd terms, cosine has even terms. Did I do that wrong before?
Yeah.
Oh, this is a disaster. They're all going to unsubscribe from me on YouTube. Oh, I'm so sorry. Here's how we fix that. I know exactly what to do. Sine. This is sine, not cosine. I'm sorry about that. The sine has the even terms. The way you can remember this, which apparently I didn't, is that sine of 0 is 0.
Wait, son.
Sine has the odd terms, yeah. Sine of 0 is 0, which is why you don't start with a 1 in sine, but in cosine you do start with a 1. I'm going to erase this all nicely so that it looks nice. No. It's easy to mix them up. I think I'm all good now. Sorry about that. Sine is the odd powers, cosine is the even powers.
Yes. The first 3 or first 4?
I said first 4, which is degree up to 3.
Oh, okay.
Because there's a constant and then.
Okay.
Right. It's true, they don't really combine.
Okay, but I need to.
Yeah, you're eventually gonna write it. okay? Yes. All right. Okay here?
I think I did too many terms, but I did like 4 terms of cosine.
Yes. Which got you 6 terms.
Yeah.
Yeah.
Wait, so for this one, I should just do 2 factors. Like how would you do that? How would you do 4 terms? Because I did 4 terms of cosine, but how would you do it?
Well, you're gonna do a long division.
Mhm.
So I would say just, like when you're doing long division, it's kind of up to you to decide when you're gonna stop. So just do it until you have 4 terms.
Oh, okay.
Yeah.
I won't need to do it.
Yeah, I don't think you actually need to use 4 terms of sine to. Okay? Yeah, great. Good there?
It's on the board.
He doesn't trust the board. I don't blame him. Can we talk about these? I see not everybody is totally finished, but that's all right. So the cosine one, pretty much everybody worked out. You start like this, and then we just distribute. So multiplying 2x gives me 2x minus 2 over 2 factorial x cubed. And then the next one, actually the next one is already going to be at x to the 5, and so I don't really need to consider any more than that. Plus, I'll just say dot, dot, dot. Sometimes when people are doing this, they say plus hot, which stands for higher order terms, meaning there is more stuff there, but I don't actually care what it is because it's not going to be part of my answer. And then separately plus multiplying by 3, we'll say 3 minus 3 halves x squared. Sorry, well, yeah, 3 halves x squared. And then the next one will again be a degree 4, so I don't care about that. And so the answer is just putting them all together. 3 minus 2x, and then I have minus 3 halves x squared, and then minus x cubed.
Isn't it
Everybody
plus
agree?
2x? Like, isn't the
Plus 2x,
positive?
yeah. The 2x is positive at the beginning. Yes. Any other concerns? Dot, dot, dot. Yeah, great. Yep.
How'd you get x3 by itself?
That's
X
here.
cubed, yeah.
X cubed, yeah. 2 over 2 factorial.
Oh, 2
Which is
factorial is
1.
2. Oh,
Yeah,
yeah,
right.
okay.
Yep. Yeah, I mean, if you leave it as 2 over 2 factorial, that's fine too.
Okay.
All right, great. And let's try the other one, which is a little more interesting. X plus 1 divided into sine x. So I'm going to write it as 1 plus x. And then here, sine x. Remember, sine x is the one which begins with x. So it's x minus, I'm going to put 0x squared plus, I guess that doesn't matter, but minus 1 over 6x cubed. That's the 1 over 3 factorial times x to the 3. And actually that's, maybe I'll need one more term. Well, the next term will be a 0 term, right? 0x to the 4. Right, that should be all the terms that I need. Maybe I'll need the next one. It can be hard to predict exactly how many you're going to need, but if you ever need more, you can just write more. If you're doing the division, you basically just do as many as you need in order to finish. Okay, this should be good enough for this long division. Everybody feel good about where we started? If you don't put those zeros in, it can still work, although you might end up confusing yourself in later steps because of the way the canceling business goes. Anyway, the first term up top, I want 1 and x shall be x, right? And then I multiply down, it says x plus x squared. We subtract, and it says minus x squared, bringing down the next term, 1/6 x cubed, all right? So actually, the quotient here, it's the first term is a 0, right? The constant in that series is a 0, but the next term, the degree 1 term, the constant is a 1. All right, I hope I'm doing okay so far. Next, I need to match up 1 with minus x squared, so that's going to be minus x squared. And then I multiply negative x squared minus x cubed, and then we subtract negative 1/6 minus 1. Negative 1/6 minus negative 1. That's negative 1/6 plus 1, which is 5/6 x cubed, like so. Right? What's my next term? Again, we are matching a 1 with 5/6 x cubed, so it's just going to be 5/6 x cubed. Bring down the next term is a 0x to the 4. When we multiply, it says 5/6 x cubed, and then plus 5/6 x to the 4. Subtract here, and I just get, I believe, negative 5/6 x to the 4. All right? And then that's my fourth term, and we'll be done. I guess I didn't need the x to the 5 term. So my last term is minus 5/6 x to the 4. I hope that any complaints about that? I think I did it right. It's easy to mess these up. There's a lot of little details in there. All right, that's it. Thank you all for a nice semester. I hope it went all right for you. I guess we'll see on the final exam. Get ready for my email and set up a time to take the quiz next week.